Good morning, everyone. Any questions anyone wants to start with? Homework 6 or Lab 6 questions? Alright, someone give me a thumbs up or a chat message or a microphone to let me know my microphone works.
It works.
Awesome, thank you. Yeah, Zoom will randomly, well, I shouldn't blame Zoom. Different things in my system will randomly change my microphone input from one thing to another, and when it changes back, the volume's down and all that, so never sure. Let's see. Homework 5, do we need to look at ENCS? Let me see what number 5 is. Oh, problem 5 from homework 5. Did I make that homework not available, perhaps? So let's see. Homework 5. So homework 5, we're trying to find a maximum frequency. So let me check this. Is homework 5 still available? Because I forgot that maybe I closed it. So let me take a look at this. Okay, that should still be available. So yeah, homework 5. We're trying to find the maximum frequency that this given machine could run at. And we don't know what the machine does. We don't know how many inputs it has. This arrow means it could be, 1 or more, or possibly even 0. It's got some outputs. There's some arbitrary combinational logic, and there's a feedback where the output of the logic feeds the input of the flip-flops, and the output of the flip-flops comes in here. And so the way we said we can analyze this is to look at setup and hold times. And the idea is, suppose the clock ticks. So we've got, boom, 1 clock tick. The outputs of these flip-flops change, right? Because they're respond to a clock event. And once those outputs change, those feed the input of the combinational logic. And this tells us how long it takes for the output of this block to be meaningful. And so we can't clock the tick until the output of this block is meaningful. So we've got to wait at least that long. But once the output of this has gotten to its stable value, the setup time requirement says, hey, we still can't clock the tick. Just because we decided this J1 input should be a 0, we can't clock the tick right then. We still have to wait. How long do we wait? That's the setup time. In this case, we have to wait an extra 15 nanoseconds before we're allowed to tick the clock. Otherwise, we've got the situation where the clock is ticking too close to a change in input. And then we're also told that after the clock ticks, we have to wait 10 nanoseconds before the inputs change. So these numbers here say 15 before, 10 after. We're not allowed to change the inputs. Well, since this logic takes 45 nanoseconds to respond to an input change, most likely this change in output will not, change the input in 10 nanoseconds. It's going to take more like, 40 or 50 nanoseconds for this input to change. So the hold time doesn't really matter. So the minimum period is usually the setup time plus the clock time. And so that can tell you the minimum amount of time from one tick to another. And then if you take the reciprocal, that'll turn it into a frequency, the maximum frequency, how often you can tick that clock. And then I think we also went through, when we did an example of this, we looked at units. And, thinking of nano as 10 to the minus ninth, how can we turn that into, something like mega, 10 to the sixth frequency? Or, you can just write this as a 45 with a bunch of zeros in the front, convert it to seconds, and then when you take the reciprocal, you'll get your frequency in hertz or cycles. And then you can, divide it down by a million and make it megahertz, or a billion and make it gigahertz, and so on. Does that make sense? Cool. Other questions? Homework or lab? So lab 6 is coming up, and that's the traffic light controller with the yellow light. And that's a weird kind of circuit you're going to come up with for that. That's different from the circuits we've done in the rest of this course. It's different from the circuits from 120, because we're introducing this delay circuit, and then we have this kind of sneaky way of figuring out what colors the lights should be by looking at a green signal and a delayed green signal. So let's see, how many equations K-maps should we have? So ultimately, you're going to have a circuit with 3 inputs. Thank you. That's your 3 car sensors and 9 outputs. Those are your 9 lights, 3 per lane. So your system diagram will have 3 arrows going in, 9 arrows coming out. And you want to give names to those that you'll use throughout. But we can't really use a truth table directly to describe, what is yellow based on those 3 inputs. It's more complex than that because this is a sequential circuit. Just because east is 1 and west and south are 0, we don't know if east is going to be green or it's going to be red. Right? If there's nothing else that's happened for a long time, then east will be green. But if there was a car that just showed up on the east, right now east might still be red, and then in 2 seconds it might be green. So we won't necessarily be writing equations in the same sense that we did in the other labs. We won't necessarily be writing sum of products, which means we may not be using K-maps. But the way that we analyzed this and came up with a design for it, we ended up with 3 columns, right? Yellow, green, red for each lane, and each of those was an output from a 2-input truth table, right? Old green and delayed old green. And so you'll come up with equations for each of those 9 outputs in terms of, some old green equation and then a delayed version of the old green. So experiment 1, you absolutely need a schematic diagram with pin numbers and part numbers and logic gate symbols and all of that, because you have to build that circuit and test it so you can use it in experiment 2. And then in experiment 2, if you want to make a block that says, delay circuit from experiment 1 with clearly labeled inputs and outputs that would tell somebody exactly how to wire up the circuit, I'm okay with that. If you don't want to repeat the 2D flip-flops, times 3, because you're already doing that in experiment 1. But you need to, somehow tell the person what pins to put wires into. And so your best bet is in your schematic for experiment 2, include the D flip-flops in that delay circuit with part numbers and pin numbers and so on and so forth. So I'm just going to go ahead and say that. Lab 6 experiment 1, you definitely need a full schematic. And for experiment 2, include the schematic from experiment 1. So I'm going to say don't try to do what I said a minute ago, a system diagram with pin numbers on it or something. Just include the 6D flip-flops, 3 chips, and pin numbers, part numbers, component ID, all of that stuff. The way you develop your circuit for this lab is super critical, right? Now, part of this lab is demoing it to me, but a critical part of your lab report is how you develop this. If you say we need to make a traffic light controller, here's the circuit, you should have some discussion in there that develops, the circuit explains how you got this, which is going to involve some of the things that we went through, the past few classes when we analyzed this circuit. Timing diagrams, truth tables, a discussion of the different states of the system, and whatever you think is going to help explain where this circuit came from and why this circuit should work. And writing a lab report is partially a way to help you understand what's going on in the lab, to help you, yourself understand why does this work, or, if it doesn't work, why doesn't it work? Because explaining something is sometimes harder than doing it. I can walk from here to, the other side of the room pretty easily. But if I tried to explain to someone who had never walked how to walk, that would be a really hard thing, right? It's not just, put one foot in front of the other. There's a lot of things you do. And if you really wanted to understand walking, well, one way to do that is to walk a bunch. But to understand it more completely, you would try to explain to somebody, how do you walk? And that's kind of what you're doing in your lab reports. You're explaining, what did I do, why, how did I do it, what was it that I learned from that, what happened when I did it, and so on. All right, so let's see. Let's talk about the delay circuit. And in particular, the 7474. And so let me pull up a data sheet. So first, let's go to ENGR250. Component specifications and go down to 7474. And most of these chips, this is not 100%, but most of these chips, this says 74LS74A. It could say just 7474. It could say 74LS74, maybe without an A. Most of these are interchangeable. And so you can, it might say 74HC74 in Tinkercad, right? But it's usually, this 74 is kind of always there. It's usually whatever number comes after here that tells us what is this chip, what does it do, and so we can find, you know, something close. But in this case, this should be the exact data sheet for the chip you have in Tinkercad. So it's two D flip-flops, and they have this preset and clear behavior. So if we drive low the preset line, that forces the output to a 1. And so if preset is low, doesn't matter what the clock is, doesn't matter what the D input is, the output goes high. If clear is low, same thing except the output goes low. And we're not interested in those behaviors for this experiment. So one thing we'll want to do is we'll want to make sure the clear and preset inputs are all tied high. So how do we do that? Well, typically run them through a 1K resistor to VCC. And I can use a single 1K resistor if I want and pull both of these up to 5 volts. And, you know, since this is a D flip-flop, we don't have a standard logic symbol for it. Generally, if we don't have a standard logic symbol, we use a box, because that's, you know, like the universal component. So this is what our D flip-flops look like. And there's usually a clock, and there's a Q, and there's a Q bar. And if I'm putting this in the schematic, right, this might be called, you know, U1, where U1 is a 74 LS 74. And we can put pin numbers on it as usual. So clear 1 is pin 1, and preset 1 is pin 4. So I can put a 1 right here and a 4 right here. And clock 1 is pin 3. So I can put a pin 3 right here. And then Q is, Q1 is 5, Q1 bar is 6. This is just Q. So that's how that component would go into my schematic. Right, and for my second flip-flop, same thing. It'll probably also come from U1, but different pin numbers. So I won't include the pin numbers here, but you should. So here's my second flip-flop, and it's got a preset 2, and it's got a clear 2, and it's got a clock, and it's got a Q, and it's got a Q bar. The goal of, so I'm working my way to the question of how we actually hook this up, but it's a good place to talk about how we actually present it in a schematic. The goal of the schematic is to be able to hand this to somebody and they can build the circuit. They can connect the right pins to the right wires. So let me just go ahead and fill these in. Clear 2 is going to be a 13, preset 2 is going to be a 10. Clock 2 is going to be 11, and then Q2, this is Q1, Q1 bar. Q2 is going to be 9, and Q2 bar is going to be 8, and then VCC is going to be 14, and ground is going to be 7 as usual. So there's the information, but before we actually wire this, let me suggest how you could rewrite this, right? The picture for a D flip-flop usually shows, you know, the clock on the left in the middle, and then Q and Q bar on the top and the bottom, and so on. But we're free to rearrange those in whatever way makes sense. And so how you might draw this for your circuit diagram could be like this. So this is going to be U1. And maybe I'm just going to take, preset 1 and clear 1 and tie them together down here. Run that through a 1 kilo ohm to VCC. And I'm not going to worry about Q1. Q1 bar. I'm just going to need Q1. So I'm going to put Q1 right here and bring that out. And over here I'm going to have my second D flip-flop. Oh, I didn't mean to draw that wire yet, but we're going to draw that wire in a second. I'm going to have Q2, I'm going to have preset 2, clear 2, and maybe I can just, run those over like that. And say these also go to 5 volts, so those are logic 1. And then my clock, well, my clock is common to both flip-flops, so I might do something like that. So this would be 3 and 11. Don't quote me on these pin numbers, because I'm doing this unrehearsed. But 1, 4, 10, 13. And then this is pin 5, and this is going to be pin 9. Alright, so that's what our wiring diagram is going to look like. But what's the logic of this? So we'll come back to this, but let's draw a block diagram. Now, block diagram is not a wiring diagram. This is a logic diagram. We've got a clock there, we've got D and Q, we've got D and Q. And we know our clocks are going to get tied together. So these will, be the clock. This is coming from the 555. So to make a shift register, the idea was let's feed something into this first flip-flop's D input, and let's take that first flip-flop's output and feed it into the second flip-flop's D input, and then take the output of that. So what does this do if this is D1, Q1, D2, Q2? And I always try to do, 1, 0 when I'm numbering things, but here I'm using the labels from this data sheet. So that's why I'm doing D1 and D2 and so on. So what does this look like? Here's the clock. And are these positive edge triggered or negative edge triggered? Dual positive edge triggered D flip-flops. So these flip-flops do their thing, whatever that is, on the rising edge. So this edge right here is when the flip-flops act however they're supposed to act. And so if I call this in and I call this out, we can make a timing diagram. So suppose my input changes right here. Alright, well, that input is also D1, input of a D flip-flop. And we know a D flip-flop, nothing happens to the output until the clock ticks. So if I change the D input here, nothing's going to change. And so let's suppose that Q1 is initially low. And we know right here, the input's 0, so Q1 is going to be low. And Q1 is also D2, and if D2 is low, Q2 is going to be low. Alright, so let's look at these events. So time continues, the clock drops. At this point, the clock is going to rise. So what is Q1 going to do at this moment in time? Is it going to change or not?
think it will change to match D1.
Exactly. It'll change to match D1 because that's what a D flip-flop does. When the clock ticks, Q takes on whatever value is coming into D. Well, at this clock tick, D is a 1, so Q is going to rise to a 1. And it's going to hang out high for a little while. What's going to happen to Q2? So Q2 is going along, it's low, it's low, it's low. What happens at this clock tick? This is the tricky / magic one.
It will be 4 seconds after Q1. Or, sorry, 2.
So just looking at this point in time right now, where this clock tick occurs, is Q2 going to change at this moment?
No, the next one.
Right? It's not going to change because at this moment, D2 is a 0. So I should have drawn a little propagation delay there. So let me cheat and make a sloppy line. Right? At the moment when the clock ticks, D2 is a 0. That's what this flip-flop samples, and it says, oh, D2 is low, okay, Q2 is going to stay low. And the magic of this is, both of these things do the same thing at the same time. And if we analyze it sequentially, let's see what this does, and let's see what that does, we might think that they both change simultaneously, but at the same moment, that same clock tick that they're both seeing simultaneously, this input is a 1, this input is a 0. So Q1 goes high, Q2 stays low. And then nothing happens until the next clock tick. At the next clock tick, the input is still high, so Q1 is going to stay high. But now something different happens. At this clock tick, flip-flop 2 says, what's my D input? It's a 1. I'm going to change my Q to also be a 1. And this is, Q2 is what we call out. So the kind of bottom line behavior is, input 1 changed here, or input changed there, output changed over here, and there was this delay. In this case, the delay was about 1.5 clock ticks. And since our tick is 2 to 4 seconds, that's, about 3 seconds. So if your circuit is not doing that, what should you do? Make sure that your clock is changing slowly. Put an LED on whatever this line is and make sure it blinks on, it blinks off, about 2 seconds per cycle. That's the first thing, because if this clock goes really fast, this will appear to happen instantly. Assuming the clock is changing correctly, put an LED on this. And what you should see is that if you change the input in between clock ticks, this light won't come on until the next clock tick. Right? So throw an LED on here. And if I set the input over here to a 1, nothing should change here until this light comes on. This thing goes positive. And then this should come on. If that's not happening, if this is turning on as soon as the input changes, either your clock is going too fast or you're not actually connected to Q1. Or maybe you didn't connect the preset and clear lines to ground. To VCC. Alright, let me go back through some questions. How much info should we show in our key? If by key you mean the component ID block, that's usually something like part, well, something like ID, and then what's the part, and where does power go, where does ground go, and which pins are not connected. So U1 might be 74 LS74, VCC on 14, ground on 7, and no connection would be, 6, 8, and whatever other pins you don't use. If you're talking about the key in our state diagram, that's a different from all of this, right? That's I'm drawing a picture that shows the state. And if there's a more output, you can list that here, and then show the transition arrows and show, the different inputs slash and your different mealy outputs, the outputs that depend on the inputs. So that's the state diagram key. How do we change the capacitor or the resistors to change the clock frequency? Well, if you, let's see, go back to the lab 5, I think. So lab 5 is the first time we use a 555, and we have these formulas that show us how long the output on pin 3 is going to be high, that's TH, and how long it'll be low, that's TL. And so the values we used in this experiment were a mega ohm for the 2 resistors, microfarad for the capacitor. And if you plug in 1,000,000 here and 1,000,000th here, they cancel, so time low is about 0.7 seconds. And RA plus RB is 2,000,000, C is 1,000,000th, this multiplier is around 2, and so time high is about 1.4. So if you build this whole monstrosity, and you only need one of these for the entire lab 7, right? You've got 3 delay circuits, they can all use this same output, so you only build this once. Putting a mega ohm on RA and RB, and then a microfarad on C, that should get you that 2 second pulse. If you want to test and you're impatient, right, you can make this capacitor half a microfarad, and it'll run twice as fast. Because if we cut C in half, these times get cut in half also. So below micro is nano, so 1,000 nanofarads would be the same as a microfarad. So if you made this 250 nanofarads, it would run 4 times as fast. It would take about half a second to go high and then low. And you can do quicker debugging, for example, with your counter circuit in the past lab. So this, wire it up with part numbers and pin numbers and component ID, block, and all of that good sort of stuff. And we're probably going to, have a block over here with a 555 and pin 3 coming out, so that's got to be included, right? Because it's part of your circuit. And then this D1 input, that's going to go through a switch that we can connect to ground. So with the switch open, this input is pulled to 5 volts. We have a 1 going in. And then this output, we can run through a 1K resistor to ground. And so when you power this circuit, the LED should turn on after a few seconds. And then to test it, close the switch, and 2 to 4 seconds later, LED should go off. And it should be a really noticeable delay. All right, these are great questions. What else? Bless you. So definitely do experiment 1 first, because you want that circuit to be working and well understood before you try to use it for experiment 2. So that you're only, trying to tackle one problem at a time. And then experiment 2 is this business of take the old permission signal, the old go signal, and take the delayed version, 2 to 4 seconds, and looking at combinations of those can tell us what color our light should be. So we get a green light after we've got permission for a few seconds. We've got a yellow light if we just lost permission but it's been less than a few seconds. And we've got a red light any other time. And from that we can make this truth table of the old permission and the delayed old permission, and the different combinations of those tell us what color our light should be. And so we can make our truth table for green, yellow, and red. But again, it's not a truth table of the car sensors. It's a truth table of the Lab 3 permission signal, the old green signal, and the delayed version of that old signal. And so for the eastern lane, right, the equation I think we found for that was eastern green was just east. And so this old green signal for the east is just, the eastern car sensor. If the car sensor on the east says, hey, there's a car here, that car gets, permission to go in Lab 3. So here, that's our old go signal, the output of the delay, that feeds the delay. The output of that is the delayed old go signal, right, or dog. And then the combinations of those tell us what color that eastern lane should see. And so do your classical analysis, find equations for these 3 outputs based on those inputs. Simplify them. This one, red in particular, will simplify nicely. And then you can sketch a diagram, implement it in Tinkercad, and you can do this lane by lane. So set this up, hook a switch up for your eastern sensor, and if the switch is open, meaning there's a car to the east, your green light should be on. And now flip this switch to a 0, and a few seconds later, green should turn off, yellow should turn on. And a few seconds later, yellow will turn off, red will turn on. So that's half the test for east. The other half is flip this switch so east is equal to 1. Nothing should happen for a few seconds. And then all of a sudden, red turns off, green turns on. And remember, lab hours are 5 to 8. They're in this regular 250 room. I'll be there tonight. So if you want to demo your circuit there, that's a good time to do it. Or if you've got problems with your circuit and you want to, screen share Tinkercad and look at what you're doing together, we can do that at that time also. We meet office hours in the regular classroom so that people can just kind of come and go. But if you want to talk one-on-one, if you've got a question on a homework or something you don't want the whole class to hear, right, we can open breakout rooms and hop into there to screen share stuff and so on. But in a in-person lab session, typically it's a bunch of people in the room with questions or working on homework, and someone might go to a board and start working on something, or I might go to a board and start helping someone with their question, and other people might kind of watch that or maybe even participate in that. And it's a different feeling from just kind of like working on homework alone. It's can be a little more collaborative and more like a one-on-one-ish version of a classroom, basically. But I don't open those hours to people outside the class, so it's just for us. All right, what else can we talk about? I got a lot of stuff I can talk about, but is that a question? I just heard a microphone open. All right. Well, I posted homework 7 on Canvas, and Lab 7 has been up there from the beginning. So we'll talk about those. What time are we? 8:40. Let's go through homework 7 and Lab 7 briefly right now. And then let's go back to talking about Verilog and looking at this Verilog tool. But let's put those questions up first so that we kind of know where we're heading. Have a great day. See you after school. Bye. All right, so let's take a look at these. So homework 7 is basically designing a bunch of circuits using Verilog, right? And so we started talking just very, very briefly about Verilog on Monday. It's this design language we can use to describe circuits, and then we can use software to take in those descriptions of circuits and either, actually configure a physical piece of circuitry to implement our design, or for us, do a simulation of the circuit we're describing. And so we can, drive the inputs of our circuit and look at what the outputs do and so on and so forth. And so all these questions in homework 7 are about writing Verilog code to perform different functions. And again, there's solved and unsolved problems, right? And I'll say again, don't go immediately to the solved problem and try to change it into the unsolved, right? That's kind of a mimicking behavior, and that can help up to a point. But if I give you a different question, you don't have a solution in front of you, can you come up with a solution on your own? That's the goal of the homework, right? So you skip the solved problem and you go straight to the unsolved one and say, can I write Verilog code to implement this function? Well, if you have no idea how to do that, right, which we haven't really done this yet, so probably you have no idea how to do that right now. But after going through some examples in class and running some simulations and so on, if you still have no idea how to do that, right, go back and check your notes. And there should be something in there after today where we implement some sort of logic function. Maybe it'll just be, f of AB equals A and B. But a version of this, right? And so you can try to reproduce what we do in class, at home from your notes and maybe from the videos. And then you can start trying to change it. And say, well, what if I wanted to do an OR gate? What if I wanted not A and not B instead of A and B? And after you do a few experiments like that on your own, now you can say, oh, you know what? I could probably do something slightly different to get not A and B and not C. And then if you can implement this and you can implement an OR, then you can say, oh, maybe I can implement, the OR of all of these. But if you come straight here and you look at this and you just say, okay, well, this was a C and I want a C bar, so I'll put a twiddle in front of that, right? You might get your homework question to simulate correctly, but you haven't learned, all that stuff that we just described. So work on the unsolved problems, and if you're stuck, right, go back through your notes. And hopefully people are taking notes during lecture, right, and not writing down everything that's said in class like a court reporter, but, key ideas or things to go back and think about, right? Hopefully you're asking questions if I start talking Greek, right, and nothing is making sense. or if something, you know, just doesn't resonate with what you thought we were talking about or what I was saying, right? So go back and look at your notes, and if not, you can go back and try to find things in the video. And if not, you could try taking a look at the solved problem to get started, right? And then try to do the unsolved. If this happens after, you know, 2 or 3 problems and you have to keep going to the solved problem, come to office hours or come to lab hours, and you know, I'm just not getting this, or I don't know how to start these problems, or I can start these problems but I don't know how to finish them, right? And that's where I can help you sort of go through these steps of working on these problems. And the analogy that I was thinking about last night is like learning to drive, right? So I'm guessing most people in here know how to drive, even if you don't have a car or don't drive, right? So how do you learn how to drive? Somebody can tell you how to drive a car. Well, put the key in the ignition and turn it till the engine starts, let go of the key, and then, you know, push the gas and turn the wheel left or right, right? Someone can give you all kinds of description. You could probably go to a 10-hour lecture on how to drive, especially in a stick shift, you know, and press the clutch down and move the shift lever. And you could watch people drive. You could watch videos of people driving. You could go online and find YouTube videos where people put their phone next to them and you can see them driving. You could read, you know, discussion boards where people talk about different aspects of driving. And you could spend 50 hours studying how to drive, right? What's going to happen the first time you sit down in a car? Are you going to be able to drive? Probably not. And one conclusion from that might be, these people don't know how to teach me how to drive, right? Oh, there's no good videos out there. There's no resources available for learning how to drive. And that's true in some sense, because you cannot be taught how to drive. You have to learn how to drive. And it's a slightly different process, right? Being taught something is, you know, the Vulcan mind meld, the thinking cap from Spock's brain, right? I say abracadabra and bingo, I know how to drive, you know, I know Kung Fu, Matrix. But learning is going through the process of doing something, not succeeding the first time or the first few times or the first, you know, 20 times, and then getting that aha. It's like, oh, okay, you know, you've got that feeling for how much you turn the wheel to make a right turn, or how you move the clutch and the gas and the stick shift to change gears smoothly on a hill. And that's what this stuff is, right? This is one reason why 250 is such a hard course. It's not just, you know, that the labs take 10, 15 hours to write up and they come every week. It's that the material itself is not just memorization. It's not, you know, here's a set of steps, follow this and you're done. I can describe how to do a K-map. I can show you a bunch of K-maps that are worked out. But until you actually start drawing the rectangles and start trying to put the labels on the rows and columns and try to fill the ones in from your truth table and try to find the rectangles and cover them and write the equations for those, it's not wired in your brain, right? And it's that wiring, it's that building of neural pathways around some set of concepts. That's what learning is. That's what you're in college for. That's what you're taking this class for. It's not to build a traffic light controller. It's not to learn how to build a traffic light controller. It's to build up those ways of thinking about problems in terms of digital circuits, in terms of Boolean logic. So all of that is kind of, you know, pep talk / motivation / whatever, to say, you know, spend your time on the unsolved problems. And if they're hard to do, that's good, right? That means you're not wasting your time. If you go to the gym and you lift the half-pound weight and you do 1,000 repetitions of that, you're not going to build muscle, right? That's easy to do for most people. You're not going to get a benefit from that. So if these are hard, if they really, really stress your understanding of a concept, that's good. That's where you want to be spending the time and the energy. If it's easy, if you can actually do this, without too much difficulty, well, that's great, because it means you know how to do, Verilog code related to making a T-latch, for example. And that's good, so go on to the next problem. And when you get to a problem that you can't do, right? Well, I don't know how to make a counter. I can do flip-flops, but I don't know how to make a 4-bit down counter, right? That's where you want to be spending your time. And if looking at the solve problem and then modifying it by changing one character from a plus to a minus gets you the solution, well, you just found an easy way to do something that was very hard. You probably did not get the benefit from it that you would have gotten if you had gone the hard path, which was, going back to your notes and reviewing it and seeing what we did in class and trying to repeat those steps yourself, making modifications to it, doing some experiments, and so on and so forth. So we really haven't done any Verilog yet. We're going to do that, the rest of today. We're going to look at Verilog code along the lines of things that you'll see in this homework. Now, you have some time before the homework is due, but you should get started on it when you can, and we'll certainly get through enough Verilog and enough of the tool today to be able to do at least these first few problems, which are, combinational logic or simpler sequential circuits, flip-flops, and possibly even a counter. All right, so that's the homework, and this will make more sense as we go through, and we can come back to this and talk about what exactly we mean by a 3 to 8 decoder, an 8 to 3 encoder, and here's your last lab 7 or traffic light experiment, right? So this is homework question 7. Write Verilog for a 3-way T intersection, and this is pretty fun. And in the Canvas posting of this assignment, it says assume you have a 2 cycle per second to 2 hertz signal available for your Verilog code. So we're giving you the 555. All right, let's do lab 7, and then we'll take a break. And I'm gonna have to get this from the website because I don't have it downloaded. Just give me one sec. So lab 7 says you can download it here. So this is a different sort of lab from the other ones. We're not using Tinkercad for this. We're using a different set of software, which is this Aldec software that we talked about last time that hopefully you've downloaded and installed by this point. And so you're using that software for this lab. And the first experiment, oh, this is a different one. So 4 experiments, and these are very much like the homework questions, right? Except the homework questions, really all we're after is the Verilog code and the simulation. So let me go back to the homework once more. So in addition to the code, include design documentation either as comments in the code or a separate document. So so we need Verilog code, right? And you've got to either explain how this code works or put comments in telling me what happens. So like this, input is driven always, so a wire type is used, and so on. For the lab, what you want is the usual material, right? The introduction to the report for each experiment, a description of what the experiment is about, what you're trying to do, how you're doing it, and so on and so forth. But for each experiment, you got to include both the code for the Verilog and the simulation output. So we're going to work with the simulator after break, and I'm going to show you how to, write up some Verilog code, compile it, run it in the simulator, and see what the behavior is. And that's going to take the form of timing diagrams that the software will produce for us. And so for each of these experiments, you're going to have to include the code, the Verilog code you come up with, and the simulation results. That's how you demonstrate what your code actually did. And so we've got 4 experiments in here. The first is to make what's called an even parity generator. An even parity means the system will take an 8-bit number and it outputs a 1 if there's an even number of 1s. Alright, so this is something related to reliable communications. So input going to be 8 inputs. I'm going to call these B0 through B7. And there's some output X. And the behavior is X equals 1 if there are an even number of inputs that are high. So for example, I have 4 inputs that are high. 4 is an even number. My output here would be a 1. I have 5 inputs that are high. 5 is not an even number. My output will be a 0. Okay, that's what your circuit for experiment 1 should do. This is called an even parity generator. And if we're sending information from one machine to another, we can, instead of sending just 8 bits per character, right, if we're using like ASCII code, instead of sending 8 bits per character, we send 9 bits. And we add this 9th bit using a circuit like this. And whenever we receive this 9-bit packet of information, we can count how many 1s we have, including this. And the result in this case should always be odd. If we had an even number of 1s in here, we're going to add another 1, which will make the total odd. If we had an odd number of 1s in here, this will be a 0. The total 9-bit packet will have an odd number of 1s. And this helps our reliability because, for example, if this bit gets changed to a 0 and we receive this, we know there's a problem. Because we'll take these 8 bits, run it through our circuit, and our output will say, hey, the output should be a 1. And if we got a 0 over here, hey, something went wrong. And so we're going to say, I didn't hear what you said, go ahead and resend that last 8-bit pattern. So experiment 1 is designing and simulating a circuit to do that behavior. Canvas doesn't like zooming. Hold on. Alright, so you're going to design a circuit, 8 inputs, 1 output. And that's the behavior of it. Now we could do this with what we know about combinational logic, but what's your truth table going to look like? It's going to have 8 inputs, 1 output, 256 rows. And if we make a K-map for this, we're going to have 256 boxes, and half of them are going to have 1s in them. And, you know, a K-map with 4 inputs we can do. With 8 inputs, we need some kind of hyperdimensional blackboard that we can draw, you know, 6-dimensional cubes on. And that's a pain. And if we just tried to write, you know, a sum of products, it's going to have 128 product terms all ORed together. So doing this with combinational logic is a pain. But doing this in Verilog is going to be relatively simple. So that's experiment 1. Experiment 2, you're going to make an 8-bit counter that can count up or down. So synchronous means there's a clock, and an up-down counter means it looks something like this. So there's a clock. It's 8 bits. So, you know, we would have 8 wires coming out. And this is, you know, X. And this is an 8-bit counter. So we've got 8 output bits, X0 through X7, that's the count. And there's an input that we can call direction. And we might say direction equals 0, count down. Direction equals 1, count up. So this is the circuit you want to build for experiment 2. It has a clock that comes in. Every time the clock ticks, the count should either increase or decrease. Which one it does is controlled by this direction input. So for example, I might say if the direction is 1, then each time the clock ticks, the count should go up. It should increase. And if the clock ticks when direction is 0, it should count down. If the count was 17, it should go to 16. And with these 8-bit counters, you know, if the count is as big as it can get, 255, and you're supposed to count up and you tick one more time, it doesn't count to 256 because that's not an 8-bit number. It will count back just to 0. So it rolls over. And if you're counting down, you get down to 0 and you tick once more to count down, it doesn't count to -1, it counts to 255. Right, a bunch of 1s. But if you look at this as a 2's complement number, that is -1. And so counting from down from 0 actually does take you to -1. Or 255. So experiment 2, you're going to write Verilog code to do that. And we can do this with flip-flops. We could do this with a state machine system, and we'd have 256 states. Right? Because 8 bits, we've got 8 flip-flops. But in Verilog, this is going to be a few lines of code. Alright, experiment 3, we're going to make a 16-bit shift register. You're doing a 2-bit shift register for experiment 1 in lab 7, or lab 6, right? Using 2 D flip-flops, making a 2-bit shift register. If you had 16 D flip-flops, you could make a 16-bit shift register. Alright, we'll add more detail to that once we get further into Verilog. And then experiment 4, you're going to use your circuit from experiment 3 to do the following kind of odd circuit. This is a circuit that detects over the past 16 clock ticks were exactly 5 of them equal to 1. Alright, what the heck does that mean? We have a clock. It's ticking. Right, so just think of a wall clock ticking. And every time that it ticks, you look at an input. And if it's a 1, you write down a 1. If it's a 0, you write down a 0. And so, you know, let's do this chalk style, right? Clock ticks, I look at the input, it's a 1. Okay, I'm going to put a mark right there. Clock ticks again, I look at the input, it's a 0. Ticks again, there's another 0. Ticks again, there's another 0. There's a 1, there's another 0, there's another 0, there's a 1, there's a 1, there's a 0, there's a 1, there's a 1, there's a 0, 0. You're counting how many zeros and how many 1s you've seen, right? And you're only remembering the last 16. I don't want my counts to go on, you know, like forever. So I'm only going to remember the last 16 clock ticks that I've seen. So that's the first thing this circuit does. It records how many ones, how many zeros it's seen each time the clock ticked. And it only remembers 16 of those. So the first thing that I saw after I've seen 17 clock ticks, I'm going to forget about the first one I saw. The next clock tick, I'm going to forget about the second one I saw. And this you can do with a shift register. Shift register basically holds the last 16 ones or zeros that you saw. The other thing you're going to do is, at any moment, if I've seen exactly 5 ones, I'm going to set my output high. I'm going to set my output to 1, meaning, hey, I've seen exactly 5 ones. If I've seen fewer than 5, or if I've seen more than 5, my output will be 0. But anytime I've seen exactly 5 ones, that's when my output goes high. So if you want a physical analogy, you have dogs and cats walking into a room. And the room holds 16 animals at a time. So here's a room. And animals can come in, animals can leave. And there's dogs and cats. So an animal comes in, another animal comes in, another animal comes in, and as they come in, they walk through. And so when the room is full, there's going to be 16 dogs and cats in here. And if another animal comes in, that first animal that came in leaves the room. And your circuit basically says anytime there's 5 dogs, exactly 5 dogs, set your output to 1. So there's a light that turns on that says there's exactly 5 dogs in the room. Okay, that's the behavior of your circuit you're after. So if there's 6 dogs, the light is off. If there's 3 dogs, the light is off. But if there's exactly 5 dogs, the light should be on. So the dogs are the 1s, the cats are the 0s. And so this thing is a shift register. We're going to each time the clock ticks, take the input and move it into the next of these 16 positions. So this is using your circuit from experiment 3, which is the 16-bit shift register. So what does the shift register do? At the rising edge of the clock, it accepts an input, it loads it in, and after 16 clock cycles, that input will appear on the output. So whatever animal comes in here, 16 ticks later, it's going to leave. And so it's like a big delay circuit. If you see a dog and a cat and 2 dogs, 16 ticks later, coming out of here will be a dog and then a cat and then 2 dogs. But if we look inside that shift register at any time, we can count how many 1s are there. And if we see 5 1s, then the output should go high. So as we design circuits in Verilog, we'll start to get a feel for how we might do some of these things. This first one's going to be a combinational circuit. It's going to be like the first few questions from the homework. This second one's going to be a counter. That's going to be like the 4th question in the homework, where we're implementing a 4-bit up binary counter. So here's an 8-bit that can go up or down. And then the shift register questions, that's what we've been going through. We'll code some shift registers in Verilog. Maybe we'll do a 2-bit shift register and get an idea from that. All right. So you've got until I think it's Monday of that final week. So this is due on Monday, June 6th. All right. So it's almost 2 weeks from today. And I know you're still finishing up Lab 6 probably, but Lab 6 is done on Friday, so you've got over a week for this, right? But I want it in by Monday so that I can grade it and we can talk about it in class on Wednesday, because that would be our last class meeting. Sorry, that was the homework I was talking about. The lab is due June 3rd. So lab will be a week from Friday. So sorry, I was confusing lab and homework. So lab is due a week from Friday, so the same schedule we've been following. But the homework you have an extra weekend in there. Let's see, what will the final exam look like, and could you tell us what to work on to prep for it and what notes to study? So yeah, let me see. So final exam, 6 double-sided pages of notes or 12 single-sided pages of notes. And you can put anything you want on those. Those can be handwritten, they can be typed, they can be computer generated, they can be miniaturized. But you know, whatever you think is critical. I don't recommend taking the entire book and reducing it to 12 pages. I don't recommend using every note you've ever taken in the class, but if you're developing notes as we go through the course and you're modifying those after using them on homework and such, you should end up with, you know, a set of notes that's good for you, which will be different from, you know, what's good for someone else. And we can run through, you know, review topics later. I haven't updated this yet. I usually talk about this the last meeting. But good practice would be, you know, going through the homework questions, making sure you understand the labs. If you go to the syllabus, up here in the top you can get the textbook. And the textbook has tons of examples, and some of them are worked out, some of them are not worked out. Right, some are you know, work on this as an exercise, and some of them show you how to do a problem. And we have not done the entire text, but we've hit most of it except for this optimization and testing section and the VHDL section. So we're not doing those. But the rest of this, you know, this was sort of review of ECS 120. This was all the combinational stuff. So sum of products, product of sums, canonical forms, K-maps, all of that stuff. This is what we were doing last week. Was sorry, that's more K-maps and stuff. We skipped some of this, some of the stuff around glitches and so on. This is the stuff we were doing last week and a bit of the week before. So analyzing state machines. This is the part we've been doing most recently, which is synthesizing state machines. The optimization stuff we have not done and will not do. And this is the stuff we started on Monday, which was Verilog as a hardware definition language. And then 9 is some miscellaneous stuff. Multiplexers, demultiplexers, adders, full adders. We have not talked about multipliers or ALUs, but you can read through those. I mean, it's a page each. And so definitely working problems, right, is the most important thing, because that's what you're going to be doing on the exam. And so the more practice you can get working out problems, right, analyzing a circuit or doing a truth table, the more familiar those things will be on the exam, right? Develop a system diagram and truth table for 2 gates that ensure only one fish leaves the outer door at any one time, right? That's a cool little design problem. You got some fish and you want to control these doors based on whether or not there's a fish in here. And the holding area has a sensor with a 2-bit output that tells you if it's empty, if there's one fish, or if there's 2 or more fish. And you have 2 outputs your circuit should generate to control these doors. A 1 opens the door, 0 closes the door. So can you design a circuit to do that? So doing that is really good practice and prep, but it's important you try to do those kind of under test conditions. Now, I wouldn't say you have to time yourself, but do those with your notes and no other resources, right? So you've got your note sheets that you've been developing, and sit down and start going through some of these problems, because problems from the past units are typical of the things that are fair game, right? And try to do them just using whatever 6 or 12 pages of notes you're planning to use for the exam, and this will help you sort of tailor your note sheet. If you got 3 pages you never look at because it was important stuff week 2, but you've done these things so many times that you remember them, take those out of your notes. And if there's new stuff that you have to keep looking up in the book or in the videos or something, put those in your notes, and then use your note sheets and try to do some of these problems in the text. So let's look at some state machine stuff. So yeah, like PLAs and proms. So example, implement this function of 6 inputs using a prom and using a PAL. Right. So this was like a homework question. This was like a question on the midterm. And so here's a solution, and there's some explanations as to how the solution comes about, and so on and so forth. And then here's the state machine analysis, and this is also a different presentation of the material, right? So Izad, he wrote this text, presents sequential circuitry from a different perspective, right? He starts with this example of circuit with feedback and delay, and he kind of develops it step by step in here. And so you can find, different presentations of the material, but it's the same material in the end, right? So there's steps in here for doing state machine analysis, and they may be different from the steps I've given you in what they're called, or maybe in the order of some of them, but it will get you to the same place. So let's look at an actual sequential circuit analysis. Sequential circuit is like a state machine. Right, so this is broken out into Mealy and Moore machines, and so here's the 5 steps for the analysis. Assign a present state variable to each flip-flop. Write the excitation input equation for each of the flip-flops inputs and external outputs. That's the equation part that we do, and then substitute those into the equation of the flip-flop to obtain the next state equations, and then put together a present state next state table using those, and then make a state diagram. So here's an example, right? They're big long circuit, 2 flip-flops, lots of logic, and assign a present state, refer to the schematic for the solution. So there's the names that were assigned to these outputs, write excitation inputs. So here's what D1 is. It's an AND of 3 things. One of them is X bar, one of them you have to trace the wire, comes from Q1 bar, and the other one, trace the wire, comes from whatever that comes from. And so D1 is X bar, Y1 bar, Y2, and so on. So this works through all of those steps, right? And then there's another example. This is with a JK based state machine. And this one is left as an exercise, right? So it outlines the steps, but you have to, write the equations yourself. So what is y1's next value? What is y2's next value? So this is kind of like the setup of question 1 in the previous homework, where I went through each of the steps and gave you a table to fill in, and so on and so forth. So don't underestimate the value of the book, right? And short answer after all of that, right? Just work lots of problems. As many homework problems as you can work, as many different ways, but working under test conditions, meaning using your notes instead of going back and finding an example online that sounds similar and then trying to change it around. And then go back through your labs and make sure you understand what was going on in the labs, because sometimes we do labs by just following steps and we don't really come away with a lot of understanding. So go back and think about what happened in the labs. And the earlier labs might make more sense now because we've done more of the things that we learned in those labs. All right, let's see. So yeah, exam is 8 o'clock to 9:50, so 110 minutes. And same as the midterm, uploaded as a single PDF file by the deadline. Cool, and thanks for posting that. All right, good. Any other questions? All right, let's do a break. And let's come back at 9:27. All right, so I'll see you back in a few minutes. We'll start playing with some software. All right. So let's do some Verilog. So hopefully people have downloaded and installed that that Aldec HDL tool, because that's what we're going to be using today and most of the rest of the course. I have one student who's running on Macintosh, and we're working out a different version of this software, something called Icarus, that can be used. But other than that, I'm guessing everybody is using Windows, and so the Aldec tool should work for you. So I had a decision to make here, right? So the Aldec stuff does not run reliably under my Windows emulator, and so I have to run it on a Windows machine. And I can either zoom from Windows and not have a recording and tagging and all of that stuff, or I can try doing what you're seeing here, which is, you know, just sort of showing you a Windows laptop. So I'm going to opt for this with the understanding that, you know, there may be some something left wanting as far as video quality. But if you've got this software and you can play along while we're doing this, you'll see what's happening, and you won't have to rely on being able to read the tiny little print that sometimes pops up on these screens. And so let me do that and try it like this. So I'll focus this once it comes up. All right, so so we've installed Aldec. So I can come in here and I can search for Aldec. I don't have desktop icons, but if you do, you'll just have an icon you can click on. So I'm going to go ahead and run this. And that's an impossible to read on screen, but it's just a statement that this is the student edition, and I agree not to, you know, make billions of dollars off of it. So splash screen, and then we get a window like this. So I'm using this quick start guide that's posted on Canvas. So let me pull this over. Go down around Lab 7, and there's this Intro to Verilog. So this is the document I'm working from today and next few days. And the lab, come over to Lab 7. Has a link to the Aldec tool if you haven't already downloaded that. And in the lab itself, there's a little note here that you want to do in the beginning. It's a one-time setup you have to do to make all of this stuff work. And that's going to be tricky to show you on my projected screen, but it's this one-time setup. Go under Tools, Preferences, Access to Design Objects, uncheck the box that's checked, and check the other 3 boxes that are not checked. And so I've already done this on my Windows system, but other than that, this should work out of the box. So so let's start a new project. So Verilog is a language. It's a language we're going to use to describe our circuits, and our descriptions will be fairly short. We might write 10 lines of Verilog to implement, you know, a typical circuit, to do some sort of logic function. So the programs themselves, the Verilog code, will be short. But when we use this software tool, the Aldec tool, we have this notion of a workspace. So a workspace is an area that we're going to have about a zillion files related to this, little 10-line Verilog thing that we write. Because we're writing a description of a piece of hardware, and a lot of work has to happen to change that description into something the computer understands in terms of, logic gates and flip-flops and so on and so forth. So we begin by saying file and saying new and workspace. And I don't know if I can focus this any better. Probably not. This is the high contrast setting on Windows, but it's actually better than the alternative. So you're going to say file new workspace. And it's going to ask us for the name of the workspace. So here's my first suggestion for Aldec. For any project you're going to do, put it in an entirely independent workspace. If you're working on Lab 1 Experiment 1, make a workspace called, L1E1 or Lab 1 Experiment 1 or something like that. Don't put more than one project in a workspace. Okay? Takes a little extra work to start a new workspace. It is worth it, because if you start getting confused about which Verilog code is actually being simulated, then you end up wasting a lot of time chasing specters. So I'm going to call this workspace test 7, right? Why am I calling it test 7? Because I don't have a test 7, I'm pretty sure. So I'm going to call this test 7. Next suggestion, tend to take most of the defaults, right? You can read them, but unless we've gone through this in class and said, make sure you change this default, right? Usually we're just going to accept defaults. So all of this stuff down here I'm not going to worry about. I'm just going to click the OK button. And this is saying create an empty design. I'm okay with that, so I'm going to say next. And then here's one of the places you have to change the default. This is asking me what language I want to use, and I have two options, VHDL or Verilog. I want to change this to say Verilog. So that's important. And then go ahead and say next. And then type the design name. Use the same name you used for your workspace. Test 7. Say next. Say finish. All right. And now we've got a different window, and what we have over here on the left is something that says test 7. I know that's impossible to read right now, but let's right click on that test 7, and let's say new, and I'm going to say new Verilog source. So it's that second option down, and now I've got a cool little wizard. I can be selective about this, I guess. I don't have to have just one focus. Alright, so here's the new source file wizard. And, this box is checked, I'm going to leave it checked. I'm not going to mess around with defaults other than that language setting. So I'm going to say next. Type the name of the source file, guess what? Test 7. This is my next suggestion. If you decide to call your workspace test 7, call everything work 7. Design name, source file name, right? Just make it all test 7. It will make life easier. I'm not going to browse. I'm not going to type a name of a module. I'm just going to put in test 7 here and say next. All right. Well, now we get to make a system diagram. So let's build an AND gate. Okay, that's a noble goal for a Wednesday afternoon. Let's make an AND gate. So what does an AND gate look like? Well, it has two inputs. I'll call them A and B, and it has an output X. Yeah, I can slow down a little bit. So whatever circuit we want to build, right, we can basically specify what the system diagram looks like in this window. And we're going to be able to pick names for inputs or outputs. We're going to be able to specify them as inputs or outputs. And this will create a framework, a boilerplate set of code that we can customize to say, hey, what do we want to have actually happen inside this box? So right now, all we're doing is saying what goes in, what comes out, right? System diagram. So we're not yet saying how does that output get generated based on the inputs. We're just naming what's going to go in, what's going to go out. So let's do a 2-input AND gate. A and B go in, X comes out. So I'll come here under name and I'll type an A. Or first I'm going to say new. And under name I'm going to say A. And so an A pops up over here, and an A, this is like ridiculously tiny. I can do it though. Alright, so there's an A over here on the input side. It's marked as an input. I'm going to say new, and I'm going to put in the name of my second input, which is going to be B. So now I've got an A and a B over here. And now I want to add an output, so I'm going to say new. And I'm going to type an X. And there's an X over here. I'm going to change the port direction to say out. And that X is going to move over to the output side. See if I can do this. There we go. Alright, so this looks like a system diagram, except there's no arrows. So A and B go in, X comes out. And I'm going to say finish. Alright, so now I've got a bunch of code. Sorry for the pukey camera work here. Alright, bunch of code in here. So it's got a title, test 7, the design name is test 7, author, it's using my email, company, I'm listing Clark, file, the date that it was generated. These are comments. So if you've done programming in a programming language, you know what comments are, right? If not, comments are things you put into a program, for example, that don't actually get used by the computer. They're just there for people who are looking at this to understand what's going on. And you can put anything in these comments that you want. The system's going to basically ignore them. So I can say, you know, description, this is sample Verilog code for an AND gate. So all of this got generated by the Aldec tool. And in particular, here's this module statement. This is how we begin the definition of a piece of Verilog code. There's a module named test 7. It has 3 connection points, A, B, and X. A is an input, B is an input, and X is an output. So these keywords, input, output, say which way the arrow goes on the system diagram. A and B, that's what we feed things into. X is what we read out of. And we have these words wire here. These are actually optional, but eventually we'll replace wire with something else called reg, and then wire will make more sense. But wire is saying basically this is just a wire. There's nothing driving this unless we connect something to it, right? It's like a wire hanging off of your proto board. Alright, so end of automatically maintained section. This is all stuff that was created. Here's another comment that says enter your statements here. So this is where we actually write our code. And we want a 2-input AND gate. We want to take A, B, and them together and generate X. And this takes exactly one statement of Verilog. So we use the keyword assign. And we say X equals, and A, and we can use an ampersand to mean logical AND. If we want to do a logical AND, we can use an ampersand. If we want to do a logical OR, we can use a pipe. And if we want to negate something, we use a tilde. So tilde is the thing usually next to the escape key or near the escape key, upper left corner of your keyboard. It's just a little squiggly line. So we're just making one line of Verilog. Let's take A and B and AND them together logically, and we'll set our output X equal to that. That's our whole program. And yeah, you can just type all of this in by hand if you want, right? So if you forgot an input, you can just say, comma C and make another input C, wire C, and so on. That screen we were on before was just kind of a wizard that generates some of this code for us. Basically, every time we write Verilog, we're going to have, some comments in the beginning listing our name and what this Verilog does. We're going to have this statement, which we don't have to worry about. We're going to say module, name of the module, parentheses, and all the inputs and outputs, and then these input or output and wire statements. That's going to be there all the time. And so rather than having to type that, we can use that wizard. But we can edit this and add things or change things as we like. And then we can make, our actual Verilog code here. Alright, so I'm going to save this, and you can go File Save, or you can say Control S. So the next thing is to compile this. So there's a tab up here that says Design, and I'm going to click that, and there's a line here that says Compile, and I'm going to click that. And I'll get a message down here. And the main thing it says is compile success. Right, 0 errors, 0 warnings, analysis time 0 seconds. And that's what we're hoping to see. So if I make a typo, like, I say ZX, I just type something weird like that, and I say design compile, right, I'll get an error. In this case it says syntax error, unexpected token, ampersand, blah blah blah, right? Well, why? Because I said assign Z and B. Well, that's not what I wanted to do. I wanted to say assign X equals A and B. And so I can say design compile, and if it comes back and says compile success, 0 errors, 0 warnings, we're good to go. Okay, well, we've written Verilog code, we've compiled it, it said it was successful. So what? What can we do with that? So let's simulate the behavior of this circuit. And so this is the nicest part of the Aldec tool. It has a built-in simulator. All right, and I have something that spells out all of these steps. If it's not on Canvas, I will post it on Canvas this afternoon, so that if you haven't been writing all of this down, that should be fine. But I'll keep going. Alright, so to do a simulation, we do the following steps. First, File, New, and we want to say New Waveform. Okay, this is super important. So first thing, File, New, and say New Waveform. And we get a window like this. Okay, next step, go under Simulation and say Initialize Simulation. The next step, it'll say select the top level design unit. So it's possible that we have several Verilog modules in this workspace. And so we need to say which Verilog module is the main one, the one that drives the whole simulation. Because we might have different modules connected together to one another. So which one do we want to simulate? So I'm going to say OK. And over here it's going to list my project, Test 7. I'm going to expand that, and towards the bottom I'll see a test 7 with a little gold star next to it. There's no way you can see that on here, but it's just test 7. I'm going to select that and just say OK. And now I've got something over here which says A, B, and X. Those are my inputs and outputs. Okay, I'm going to take these and I'm going to drag and drop them. Where'd my mouse go? I'm going to drag and drop them from here into this middle panel, like so. And I'll improve the zoom once I do this. Alright, so I've got A, B, and X right here. This is going to generate timing diagrams for me. And if you look at the top of this window, these are time units. These are picoseconds. So up here we're seeing 400 picoseconds, 800 picoseconds. This point right here, this is 1,000 picoseconds. That's 1 nanosecond. This is 2 nanoseconds. So this is a super, super fine detail and time simulation. And what we're going to do is we're going to see, you know, when A changes and B changes, what does this output X do? Alright, so we got one more step we have to do. We need to say, how should we change A and B? So remember, when we make timing diagrams, our goal is to show, you know, how one thing changes relative to another. Invalid plus access switch. So that's that thing in red in the other lab that you need to set up. So design settings, simulation, access to design objects. Uncheck this box and then check these 3 boxes. And that's one time for forever. Once you do that once, it should be good to go. And that basically gives you access to changing the inputs. I'm thinking that's what that error is that you're mentioning. Welcome. Alright, so to make a timing diagram, we have to say what should the inputs be. So we're almost out of time, so I'm going to do this a little more quickly. And like I say, I'll post some descriptions of this later on today. So I'm going to right click on this and I'm going to say set stimulus. And I'm just going to take the defaults. That's my main mantra. And I'm going to make this a clock that drives input A. And it's going to drive input A at 100 nanoseconds. So every 100 nanoseconds input A will switch between high and low. So I'm going to say OK. Now I'm going to right click on B and I'm going to say set stimulus. I'm going to take the default here. I'm going to leave it as a clock, but this time I'm going to drive input B twice as fast. I'm going to make the period 50 nanoseconds. So every 50 nanoseconds B will change high, low, high, low. Every 100 nanoseconds A will change high, low, so they'll be out of sync with each other. This is going to give me different combinations of A and B. Alright, so how do I run this? There's a little window up here that says 100 nanoseconds. And immediately to the left of that is a little triangle. And if I hover over that, it says run for, parentheses, F5. That's the button I'm going to use. And so I'm just going to click that once. And I start getting some timing diagram information. So I'm going to click this like 5 times. Click it once more. And let's take a look at what we've got here. I need to change the colors on this so that they're not black on white. Oh, that's rasterizing horribly. Hold on. You gotta take my word, this is a glorious timing diagram that's been generated. Alright, we'll just come at it at an angle. So if you can actually see this, I will fix the colors on this next time to make this black on white. But the effect is I've got 3 timing signals here, and the first one is modulating up and down fairly slowly. The second one is modulating twice as fast, and the bottom one is showing me an AND operation. So here we can see it a little better, right? So this first input is A, this second input is B, and my output X is 1 exactly when both of my inputs are 1, and it's 0 any other time. And so that's a simulation of our Verilog module. Okay, those are the basic steps, and I have a quick start. I think I put it on Canvas, but if not, I'll post it and I'll send an announcement that goes through each of those steps that we just did, including setting up those design access checkboxes, and then, you know, doing file, new waveform, simulation, initialize simulation. I'll post a document that specs those out. So if you didn't catch all of that, you can read it from there. But that's it. That's the whole start to finish example. And every circuit you do is going to be basically the same thing. You're going to start with a new workspace, make a new Verilog module, go through the wizard, set up inputs, outputs, type in your Verilog code, save your file, compile it, initialize a simulation in a new waveform, add stimulators to drive your inputs, run the simulation, see what the outputs are. It takes a long time the first few tries. After a while you'll be doing this with your eyes closed. It just becomes a habit. And then you get to concentrate most of your energy on that one piece in the middle of writing the Verilog code and trying to get that to do whatever your circuit's supposed to do. Alright, we are past time. Thanks for sticking around a few extra minutes. Come by office hours, come by lab hours at 5 if you like. That's in the regular 250 classroom that we're in right now, or office hours Thursday morning or Friday morning. There's lots of other ways to simulate the circuit, and there's other ways to do Verilog. So the other suite that I like to use for this course sometimes is called Icarus, and it comes with a simulator called GTK Wave. And if you're on OS X, we can talk about how to set that up. And if you're on Linux, it also works really well in Linux. Alright, that's all I got. Have a good afternoon. See people next time. And take care. Bye. You're welcome.